In this video, we discuss learning outcome number 3 of lesson 9.1, which is about testing a claim about two proportions using the critical value method, also known as the traditional method. We've already outlined how this works. In this video, we're just going to work through an example. Just as a brief review of how this works, the p-value method and the critical value method start in the same way. We start by checking the requirements for testing a claim about two proportions. So we need to have two simple random samples. We need to make sure that those samples are independent, and we need at least 5 successes and 5 failures in each sample. We talked about this in more detail in the last video, which covered the p-value method for two proportions, Now that last requirement implies that a normal approximation to the binomial distribution is appropriate. Then we write the claim in symbolic form and use that to infer the null and alternative hypotheses. Then we identify or compute sample proportions and sample sizes. And then we graph the sampling distribution of P1 hat minus P2 hat, assuming that the null hypothesis is true, and then label the sample statistic P1 hat minus P2 hat on the graph. Then we use the assumption that the null is true to compute an appropriate standard deviation in terms of this sample or the pooled sample proportion. And then we are looking at that sampling distribution of P1 hat minus P2 hat, and we're asking ourselves, is the value of P1 hat minus P2 hat that we have an extreme value? Is it significantly high or significantly low, given that the null hypothesis is true? In order to determine whether it's significantly high or low, we compute a test statistic. Now, here is where the critical value method and the p-value method diverge. Those first 4 steps are going to be the same no matter which method you use. But with the critical value method, after you've computed your test statistic, you need to determine whether the test is two-tailed, left-tailed, or right-tailed, and then sketch and shade the critical region. The critical region is an area in either one tail or two tails that is equal to that significance level alpha. If it's a left-tailed test or a right-tailed test, you're going to have alpha area in that left tail or right tail. If it's a two-tailed test, you're going to split that alpha area into two tails. So you'll have alpha over 2 area in each tail. Those areas, that area or those areas constitute what's called the critical region. Then you'll find the critical values. Those are the z-scores that separate the critical region from the region that's not critical. The region that's not critical consists of an interval of test statistic values that are likely to occur just due to chance, given that the null hypothesis is true. Any test statistic values that are in that critical region, we would say are unlikely to occur due to chance. They're significantly high or significantly low. So we're going to find the critical values. Those are the z values that separate that critical region from the rest of the area under the graph. And then we're going to make a decision. So you're going to look at your test statistic and your critical region, and you're going to say, based on where that test statistic is, we should either reject the null or fail to reject the null. If the test statistic is in the critical region, that means it corresponds to a significantly high or significantly low value of P1 hat minus P2 hat. So in that case, we're going to reject the null hypothesis. Now, if the test statistic is not in the critical region, then we're saying that that value of P1 hat minus P2 hat is likely to occur given our assumption that the null hypothesis is true. So we're not going to accept the null hypothesis, but we're going to fail to reject the null hypothesis. In other words, we're saying that the null hypothesis might be true. We don't have enough evidence to reject that hypothesis. And then once we have made a decision whether to reject or fail to reject the null, we're going to use that to state a conclusion about the original claim in non-technical terms that everyone can understand. So in this video, we're going to solve this problem again. We solved this in the last video using the p-value method. Now we're going to solve it using the critical value method. I'll read this to you. Now, the first 4 or 5 steps are the same as the first 4 or 5 steps for the p-value method. So I'm going to go through those relatively quickly. If you'd like to watch me go through those in more detail and give you more explanation for why we're doing what we're doing, you might want to watch the video about the p-value method that will expand on the explanations for those first few steps in the method. Okay, so the problem statement says, in a study of Burger King drive-through orders, it was found that 264 orders were accurate and 54 were not accurate. For McDonald's, 329 orders were found to be accurate, while 33 were found to be inaccurate. Use a 0.05 significance level to test the claim that Burger King and McDonald's have the same accuracy rates. Use the critical value method, with a normal distribution as an approximation to the binomial distribution. Here we want to identify the null hypothesis and alternative hypothesis, and the test statistic. And then once we have the test statistic, now rather than finding the corresponding p-value, we're going to find the corresponding critical values and sketch that critical region and then see where our test statistic lies. Is it in the critical region or not? Once we have graphed that, we can state a conclusion about the null hypothesis, as well as a final conclusion that addresses the original claim. So first thing we need to do is check the requirements. We can assume that both samples are simple random samples. The samples are independent. There is no pairing between orders at McDonald's and orders at Burger King. And we have at least 5 successes and failures in each sample. So it's appropriate to use a normal distribution as an approximation to the binomial distribution. Then the next thing we need to do is identify the null and alternative hypotheses. The claim was that Burger King and McDonald's have the same accuracy rates. So the claim is that the first proportion is equal to the second proportion. If that's not true, we would just write P1 is not equal to P2. The one that does not contain the condition of equality is the alternative hypothesis. And then, so that means our alternative hypothesis is that P1 is not equal to P2. To get the null hypothesis, we just change that not equal to sign into an equal sign, and that happens to be the claim. The next thing we do is we compute P1 hat and P2 hat. So we take the number of accurate orders at Burger King and divide by the number of orders at Burger King, and do the same thing for McDonald's. Notice that they did not tell us how many orders we had from each of the restaurants. They told us how many inaccurate and accurate orders we had. So you actually have to add the 264 and the 54 to get the total number of orders from Burger King. And you have to do the same thing with the 329 and the 33. You have to add those together to get the total number of orders from McDonald's. Keep that in mind. You're not always taking the smaller number and dividing by the larger number here. You really want to think about what those numbers mean. After doing that computation, we got P1 hat and P2 hat. Okay, now we want to graph a sampling distribution of P1 hat minus P2 hat, assuming that the null hypothesis is true. So we're assuming that P1 is equal to P2, which is the same as assuming that P1 minus P2 is equal to 0. Okay, so I'm graphing a distribution of P1 hat minus P2 hat. Well, if P1 hat and P2 hat both have normal distributions, then P1 hat minus P2 hat will still have a normal distribution. Now, if we're assuming that the null hypothesis is true, what that's telling us is that that mean of P1 hat minus P2 hat, which is equal to P1 minus P2, the difference between those true population proportions. Well, if the null hypothesis is true, it's telling us that that is equal to 0. So the mean of this distribution of P1 minus P2 is equal to 0, which is the same as saying that we're assuming that P1 and P2 are equal to each other. And then we're asking ourselves, if P1 and P2 are equal to each other, is it common? Is it likely? Is it significant that P1 hat minus P2 hat for our samples is negative 0.07865 approximately? Is that significantly high or low? If it is significantly high or low, we'll throw out the null hypothesis. If it's not, we'll say that the null hypothesis might be true. Okay, in order to determine whether that P hat 1 or P1 hat minus P2 hat is significantly low in this case, we need to compute the corresponding test statistic. That requires finding the pooled sample proportion P bar, because when we're assuming that P1 and P2 are equal to each other, we're assuming that they have a common value. Now, we have an estimate for P1, that's P1 hat, and we have an estimate for P2, that's P2 hat, but those are not equal to each other. The best estimate that we would have for a common value of P1 and P2 is what's called this pooled sample proportion P bar. So rather than looking at the number of accurate orders from and dividing by the total number of orders from McDonald's and then doing the same thing with the other restaurant, we're saying how many orders did we have that were accurate in general? Out of how many total orders did we have in general? Not taking which restaurant it came from into account. That's P bar. That's our pooled sample proportion. So if we add the number of successes in each group and add the sample sizes of each group, we get 593 accurate orders out of 680 orders, which is a P bar of approximately 0.87. So that is our best guess of what P1 and P2 are both equal to. And Q bar is just the complement of that. So once you have P bar and Q bar, you substitute those into the formula for our test statistic Z. This is just going from that sampling distribution of P1 hat minus P2 hat to a standard normal distribution, assuming that the null hypothesis is true. And you could enter all of this into your calculator, or you could use something like Excel to compute this, and we get a z-score of negative 3.06. So what that's telling us is that the value of P1 hat minus P2 hat we got in our original sample, or in our sample, is 3.06 standard deviations below the mean, provided that the null hypothesis is true. That's quite a few standard deviations below the mean. We want to know if that's statistically significantly low. So we're going to figure that out. Now, not using p-values, but critical values. So this is where the critical value method and the p-value method diverge. Oh, and this slide is just showing you that we're going from the sampling distribution of P1 hat minus P2 hat to the normal distribution, standard normal distribution for Z. But this P1 hat minus P2 hat corresponds to this test statistic Z equals negative, approximately negative 3.06. Okay, so now we want to go to the critical value method. Now, with the critical value method, you always have to determine whether the test is two-tailed, left-tailed, or right-tailed first, because you might have one critical value if the test is left-tailed or right-tailed, or you might have two critical values. Since our alternative hypothesis says that P1 is not equal to P2, that tells us our test is two-tailed. So we're going to have two critical values and two parts to our critical region, one in the left tail and one in the right tail. To find the critical values, which can be denoted by plus or minus z sub alpha over 2. These are the z-scores that have an area of alpha over 2, or 0.025, to the right for that high one, and then to the left for the negative z sub alpha over 2. The alpha level is 0.05, so we're taking that, and because it's a two-tailed test, we're splitting it into two tails, so that 5% of the area, we're going to split it into 2.5% of the area in one tail, 2.5% of the area in the other tail. So that means that the area to the left of our critical value is 0.9750. Now you can find the corresponding critical value either using Excel or table A2, but note that you want to find the area to the left of 0.9750. In the body of the table and find the corresponding z-score. Then using table A2, we get z equals plus or minus 1.96. You get z equals 1.96, that's your top z-score, that's on the right side of your standard normal distribution, and z equals negative 1.96 separates that bottom 2.5% of the area from the top 97.5% of the area under the curve. Let me show you how to do this using table A2. So we go over here and we're looking for 0.975 in the body of the table. And there it is right there. The corresponding z-score is 1.9. This is 1.90, 1.91, 1.92, 3, 4, 5, and 6. So this corresponds to a z-score of 1.96. As it's stated, or as we showed on the slide over there. Now the other option is to use Excel to find those critical values. So the critical value would be z sub 0.025, which can be found using this norm S inverse function. And then we're going to have a positive version of that number and the negative version of that number because we're separating that alpha over 2 area in both the left tail and the right tail. So let me show you how to do this in Excel. Alpha in this case is 0.05. And z sub alpha over 2 would require us to use the norm S inverse function. So it's norm.s.inv, and then it asks for the probability. That's the area to the left of that top critical value. So we want 0.975, or in terms of our alpha, because it was a two-tailed test, it's going to be 1 minus alpha divided by 2. Because you're taking alpha over 2 is in that top right tail. And so we get that value, and the critical values are plus and minus that because we're talking about the left and right tail and their symmetry with our standard normal distribution. Okay, now let's go back to our slides. Okay, now that you've got your critical values of z, and we also have the test statistic z, we compare the absolute value of our test statistic, that negative 3.06, to the absolute value of those critical values, plus and minus 1.96. Since the absolute value of our test statistic is greater than the absolute value of the critical value, so we've got 3.06, which is greater than 1.96. Our test statistic is more extreme than the critical value, or in other words, it's farther out in the tail. So we're going to reject the null hypothesis. Okay, so I've graphed this for us here. I just wanted you to see that if my critical values are negative 1.96 and positive 1.96, our critical regions are this region up here in that tail, and this region over here in this tail. So when we're looking at the absolute value of the test statistic, and we're looking at the absolute value of the critical value, what we're really asking ourselves is the test statistic farther from 0 than that critical value is? If it's farther from 0, that means it's farther out in the tails. So since our absolute value of the test statistic is greater than the absolute value of the critical value, another way of saying that is that the test statistic is in the critical region. So our test statistic is more extreme than one of the critical values. So we're going to reject the null hypothesis. Oops, let's erase that. There we go. Okay, so we're rejecting the null hypothesis, but that doesn't say anything about the original claim. So now we need to state something about the original claim. Our original claim was that the accuracy rate at the two restaurants are equal to each other. And if that's not true, this alternative hypothesis is true. Now, if we are rejecting the null hypothesis and the claim is the null hypothesis, we're rejecting the original claim. So when we reject the null hypothesis, what we're saying about the original claim is that we have sufficient evidence to reject the claim, or there is sufficient evidence to warrant rejection of the claim that these two restaurants have the same accuracy rates. Now, I just wanted to remind you one more time that the critical value method and the p-value method are going to get you exactly the same result. So the p-value method, you're computing probabilities and comparing them, and with the critical value method, you're comparing the absolute value of a test statistic to the absolute value of a critical value. Or alternatively, you're graphing a critical region and looking at where that test statistic lies. The area in the tails beyond those two critical values, z equals 1.96 and z equals negative 1.96. Sorry, I've got a little typo there. It says 1.95. That was definitely supposed to be 1.96. This yellow area is given by alpha. It's 0.05. Now, if we take the area to the left of our test statistic, z equals negative 3.06. So that's this area out beyond negative 3.06. It turns out that that area to the left of that is 0.0022. So the critical region is this yellow region, and the area of the critical region is equal to alpha. and our test statistic corresponds to a p-value of 0.022, which is also an area, but this time the area is this. It's the area beyond z equals negative 3.06. So it's the probability that z is equal to negative 3.06 or less than that, or the probability that we would get the same value but on the other end. Sorry guys, I'm having trouble getting my cursor back. Every once in a while, this acts up a little bit. Okay. This is what I wanted to do. There we go. So there's negative 3.06, and we've got the area beyond that. We're going to go to positive 3.06 over here and compute the area beyond that. And it turns out that the area on the left side is 0.002 or 11. And then if we double that, we get the area on both sides that corresponds to z values or z test statistic z as extreme as ours or more extreme than ours. And we get this p-value of 0.022. Trying to get my cursor back again. There we go. All right. So we can look at this in one of two ways. We can say that since the test statistic z is in the critical region, we reject the null. Or in other words, since the absolute value of the test statistic z is greater than the absolute value of those two critical values, we reject the null. Or we can say since p, that's that blue area, is less than or equal to alpha, that's the yellow area, we're going to reject the null. But either way, we reject the null. So you see with the critical value method, we're comparing values on that horizontal axis. And we're saying, you know, which ones are farther out. With the p-value method, we're comparing areas under curves, and areas under the curve correspond to probabilities. And we're saying if it's associated with a smaller area, or if our test statistic is associated with a smaller area, we're going to reject the null. But whether we compare the areas under the curve or the corresponding test statistics, we're going to get the same answer. Because when the test statistic is farther out, the area beyond that test statistic is smaller. So when the absolute value of z test is greater than the absolute value of this critical value of z, when that happens, the p-value will be less than or equal to the alpha value. And vice versa, if it was going the other way, if we happen to fail to reject the null for a particular example. So I want you to see again that one is just comparing probabilities, the other one's comparing values on the horizontal axis, but either way we're doing the same thing and we're going to get exactly the same answer. So that is the end of our discussion of the critical value method. I'll see you in the next video to discuss our next learning outcome.